Picture yourself soaring through the sky at 35,000 feet, comfortably seated in an aircraft. The plane is constructed from layered composite materials, a cutting-edge innovation that combines strength and lightness. But have you ever wondered about the resilience of these materials? What happens if they are pushed to their limits? While rare, an example of a disastrous event occurred in 2001 with American Airlines Flight 587. The aircraft's vertical stabilizer, crafted from multi-layer composite materials, experienced a failure shortly after takeoff. The inquiry concluded that the composite material had been subjected to high stresses. This tragic incident highlights the significance of understanding the potential modes of failure in layered composites. So fasten your seatbelts and let's embark into this intriguing world of layered composites and their modes of failure. Ready? Let's get started. Unlike homogeneous materials like metals, layered composites have a unique structure that adds layer of depth to their complexity. Firstly, layered composites are anisotropic. This means that their mechanical properties can change based on the direction in which they are measured. Metals, on the other hand, are typically isotropic, with uniform properties in all directions. So when interpreting results, we must consider the directionality of the properties in layered composites. Next, we have layer interactions. The way different layers interact in a composite can significantly influence the overall properties of the material. Factors like delamination, where layer separates from each other, can greatly affect the strength and durability of the composite. This is a stark contrast to metals, which are homogeneous and do not have this layer interaction. The failure modes in layered composites are also more complex than in metals. While metals typically fail due to yielding or fracture, composites can fail due to a variety of mechanisms including fiber breakage, matrix cracking, and delamination. This complexity must be considered when interpreting results. Layered composites can also be more sensitive to environmental factors like temperature and humidity. These factors can affect their properties and performance and must be taken into account when interpreting results. Lastly, the properties of layered composites can be significantly affected by variations in manufacturing process. Factors such as alignment and distribution of the fibers, the quality of the bonding between layers, residual stress development during curing, and the presence of defects all play a crucial role. So as we delve deeper into the world of layered composites, we realize that interpreting results is not just about numbers, but about understanding the unique characteristics and behavior of these remarkable materials. In certain instances, the alignment of composite layers may make it impractical to anticipate the onset and propagation of crack during large-scale finite element analysis models. Take a look at the images on your screen. This designated area is devoid of fiber and is composed only of resin. This makes it a potential site for the development of cracks. Micromechanical models are designed to consider such scenarios. Even though it's impractical for a large-scale simulation, it's possible to construct a detailed model with the void explicitly modeled, which can be used to predict this type of failure. Certain aspects of micromechanics are attempted to be explained by specific failure theories. Representative volume elements, or RVEs, and other micromechanical models are capable of this. In fact, Ansys' LSDANA solver has certain multi-scale characteristics that are designed to be useful in this kind of circumstances. So while FEA can predict failure if it's modeled at the fiber metric scale, it typically requires very detailed modeling to capture accurately, and this is not always practical. Let's now delve into the complex realm of failure modes. These are the mechanisms through which materials succumb to stress, and understanding them is crucial to the design of robust, resilient composite materials. Firstly, we examine failures that occur within a layer. Visualize a layer of composite material, comprising fibers embedded within a matrix. Under applied stress, which may be tensile or compressive in nature, these fibers or even the matrix may sustain damage or even experience complete failure. To mitigate these issues, we applied failure criteria during the post-processing stage. This allows us to identify and evaluate potential weak points. Additionally, we can employ progressive damage models, which track the initiation and evolution of damage over time. Next, we consider failures that occur between layers, often called delamination. This involves layers of composites separating due to failure caused by transverse shear and normal stresses. To address this, we examine the interlaminar stress output, which provides valuable insights into these stresses occurring between the layers of the composite. We can also utilize cohesive zone model or VCCT models. These models can help us to predict the onset and propagation of delamination. Let's explore failure criteria for materials. For isotropic materials, the von Mises stresses and stress intensity are the two commonly used criteria. However, for orthotropic material, there are additional failure criteria to consider. This criteria apply to all orthotropic materials, not just composites. There are several common failure criteria for composites that can be specified. This include but not limited to the maximum strain, maximum stress, Tsai-Hill, Tsai-Wu, Hashin, Puck, LaRC, Cuntze, and even user-written failure criteria. It is important to note that all these failure criteria assume that the material is linearly elastic. Interestingly, the commonly used form of the Tsai-Wu criteria reduces to the von Mises criteria for isotropic materials. Note that these criteria are assumed to be orthotropic, so you, as the user, typically must specify failure stresses or strains for all directions. It's important to keep in mind that specifying a large stress or strain at failure in any particular direction effectively prevents a stress or strain from being critical in that specific direction. Let's go into more detail about a few of the failure criteria. We have many different failure criteria. Therefore, in order to make things simpler, we decided to put them into three groups according to how similarly they evaluate failure. For the first group, we'll look into the failure criteria that consider stress in single direction and no interaction between stress components. In this group, we have maximum strain failure criteria and maximum stress failure criteria. Both these failure criteria are determined as the ratio of actual strain or stress to the allowable strain or stress, strength respectively. Simple, right? And the simplicity is indeed one of its advantages. However, both these criteria have their drawbacks, as both do not account for combined loading conditions. Despite these limitations, both these criteria are widely used in preliminary design calculations and for materials where stress in any direction should not exceed the strength of the material in that direction. For the second group, we will look into the failure criteria that consider interaction between stress components. Let's look at Tsai-Wu criteria, which stands out due to its close relation with experimental results, making it a reliable tool for predicting material failure. One of its strengths is that it considers the interaction between different stress components, which, while making it more complex, also enhances its accuracy. This complexity, however, can be a double-edged sword. It makes the Tsai-Wu criteria more challenging to apply and requires more information about the material properties, which may not always be readily available. Tsai-Hill criteria is conceptually similar to Tsai-Wu criteria in accounting for interactions between stress components. For the third group, we have the failure criteria that account for different fiber and matrix failure modes separately. Puck failure criteria can be a part of this group. It is particularly useful for predicting the failure of fiber reinforced composites. It considers different failure modes, taking into account the interaction between fibers and the matrix. However, it is complex to apply and requires detailed information about the material properties. Hashin criteria and LaRC criteria are conceptually similar to PERC in accounting for fiber and matrix failure modes separately. Now that we have introduced a few failure criteria, let's just compare two of them, maximum stress and Tsai-Wu. As you can see, the maximum stress has straight lines for the strength, indicating that it doesn't account for interaction between different loading directions. Contrastingly, the Tsai-Wu shows interaction between different loading directions. It is evident from the highlighted portion of the graph where the curve deviates from a straight line. Experimental test results typically demonstrate the interaction of strength between different loading directions. This means that the maximum stress criteria can be somewhat unconservative for some loading combination. It is very important to note here that each of these criteria has its own strength and weakness. The choice of criteria depends on the specific characteristics of the material, loading conditions, and should comply with any necessary standards or methods at your organization. If you are unsure which failure criteria to use, specifying more than one and using the worst of them can be a conservative approach. Ansys Composite Prep Post permits the checking of multiple criteria concurrently and reporting the worst for the particular location. In addition to the failure criteria discussed before, there are some unique failure criteria for the failure of sandwich composites. Let's briefly explore those here. First up, we have core failure. This criteria predicts the failure of core materials in sandwich structures due to the interlaminar shear and normal stresses. It's assumed that the core failure is highly dominated by the out-of-plane stresses, so the in-plane terms are often neglected. Next, we have face sheet wrinkling. This is a local instability phenomenon where this face sheet, which can be considered to be the plates on an elastic foundation formed by the core, starts to wrinkle. Lastly, we have shear crimping failure. Although it's a local failure criterion, it describes the form of a general overload buckling failure. It applies to cases where the wavelength of the buckles is very small compared to the global buckling due to a low core shear modulus. The crimping of the sandwich occurs suddenly and usually causes the core to fail in shear at the crimp. Let's now look into some of the failure indicators in a layered composite material. First up is the First-Ply-Failure or FPF indicator, which is a single mathematical equation that signals the first failure of a ply in a composite material. It can indicate various failure modes such as fiber tension, fiber compression, matrix tension, and matrix compression. This indicator helps us determine the reserve factor, inverse reserve factor, or margin of safety. Essentially, we have a simple scalar indicator that tells us failure or nor failure and even the margin in the design. Most composite structures have numerous layers, and it is highly convenient to simplify the strength analysis into a single number at the critical location. One can then drill into understanding at the local what layer, what criteria, and also direction that are critical. We'll delve deeper into these First-Ply-Failure methods in our next lesson. The Last-Ply-Failure or LPF involves further loading beyond the FPF until the ultimate failure of the laminate. In Ansys, the analysis of LPF typically involves the use of progressive damage analysis, which involves damage evaluation based on the instant material stiffness reduction as well as continuum damage mechanics. Here, continuum damage refers to the overall process of damage evolution in materials. These solutions are nonlinear in nature. The failure indicators are related to the material's residual strength and the ability to predict the ultimate strength of the composite after damage has occurred. It's important to note that depending on the layer and the method of loading, a laminate that fails as First-Ply-Failure may still be able to sustain additional loading and have reserve capacity. However, damage is undesirable, especially if the product will undergo repeated loading, as damage can propagate and coalesce. A single-use composite article may be able to be designed with some damage tolerable as the structure will not undergo repeated usage. Understanding the relationship between failure indicators provides a framework for predicting the failure behavior of composite materials at different stages. From the initial damage indicated by the First-Ply-Failure to the ultimate failure indicated by the Last-Ply-Failure. Finally, let's explore two other key types of failure in composites: delamination and debonding. Delamination typically refers to the interface failure between two plies. This is driven by normal stress in the thickness direction and shear stress parallel to the plane of layers within the composite. Delamination can start small and grow with repeated loading, compromising the structure and leading to catastrophic failure. Delamination can also be difficult to detect since the failure is subsurface and spatial inspection techniques are required to check the structural integrity of the composite. Delaminations can originate from impact damage or even during manufacture if foreign material or contamination between the plies is present. Debonding, on the other hand, typically refers to the interface failure between laminates, between a laminate and mating part, or even between the face sheet and core of a sandwich structure. Structures that are bonded together, such as with adhesive, can experience failure at the interface. In the case of sandwich structures, debonding is most predictable when the core and the face sheets are modeled separately, such as the debonding interface can be properly modeled. Numerical techniques to simulate delamination and debonding include cohesive zone modeling, as well as the virtual crack closure technique. In this video lesson, we have explored how the interpretation of results in layered composites are different due to their unique properties and complexities. The results obtained aren't just numbered, there is more to it and how we understand layered composites' unique behavior and characteristics. We have delved into the intricate mechanisms of material stress and the importance of understanding those mechanisms in creating robust, resilient structures. We also looked into various failure modes, including fiber breakage and matrix cracking, as we discussed the importance of failure criteria. We discovered the significance of First-Ply-Failure and Last-Ply-Failure indicators, and the role of progressive damage mechanics in predicting the failure behavior. Finally, we touched upon delamination and debonding, which are the two additional key types of failure in composites. This has been a thrilling ride for anyone interested in layered composites. I hope you found this video informative. Thank you for watching.